Hey folks! Today we are going to discuss four distinct but interrelated topics: scope, scope and lifetime, referencing environments, and named constants. Some of you may have heard of these topics before, or perhaps not, but one thing's for sure: given we're all computer science students here, we've definitely encountered these four concepts in some form while we coded. So, let's get started, shall we? My name's Zarina Julia Selgas, and I will be talking about scope. It's a pretty vague word if put on its own, since it could mean a lot of different things if we go ahead and consult a dictionary. Scope could mean range, or it could refer to a slang for telescope, or even refer to that thing you put in guns when playing FPS games. In computer science, however, it is defined as the area of the program where an item's name binding is valid. Said item is often a variable, though it can be a constant or a function or basically anything that has an identifier. In simpler terms, the scope of an entity is the range of statements in which the entity is visible, and an entity is considered visible in a statement if it can be referenced or used in that statement. Let's have a more visual representation of how scopes work. Okay, suppose we have this simple C++ program for adding and subtracting two numbers. We've got two functions, the add and the subtract functions, and we have two variables within these functions, which are the sum and diff. Let's ignore the fact that the two functions have the same parameter names. We'll get to that later. For now, let's focus on the variables sum and diff. Now, in this example, we can say that the scope of the variable sum extends only in the statements found within the body of the function add. Ergo, the variable sum is only visible inside the function add. It cannot be referenced in the functions subtract and main. Similarly, the variable diff is only visible within the function subtract and cannot be called in the functions add and main. Now, let me show you what happens if we try to reference an entity outside of their scope. Okay, suppose we type in cout sum in the main function. Okay, then let's compile it, see what happens. Okay, so as we can see, an error message pops up. It's most likely something you guys have encountered before. It says that sum was not declared in this scope. The scope being referred to in this message is the main function. As we've discussed before, the variable sum is only visible in the function add, since that's where it was declared in. To include the variable sum in the scope of the main function, we would have to declare a variable called sum in the main function, like so. Int sum, and let's give it a value of 5 or something. Alright, so now let's try to compile the program again and see what happens. Okay, so the program outputs three numbers, 6, 2, and 5. So the number 6 is the output of adding the two numbers 2 and 4. And 2 is the output of subtracting the numbers 5 and 3. Finally, the number 5 is basically just the value of the variable sum within the main function. Okay. So, now the main function has a variable called sum with a value of 5. But wait, I'd like to ask y'all a question. Is this variable, this one, is this variable the same as this variable? Do they have the same value as well? The answer is no. They're completely different entities, and that's because of a certain scoping rule, which says that an entity declared in the scope of another entity is always a different entity, even if their names are identical. Let's go back to the identically named parameters of the add and subtract functions. That would be int x and int y, both in add and subtract. I'll ask you guys again, are they the same parameters? Do they have the same values? Do they hold the same values? Again, the answer is no. The x and y pair of the add function is different from the x and y pair of the subtract function, since they were declared in different places and therefore have different scopes. This brings us to another scoping rule, which says that the scope of an entity is the program or function in which it is declared. Again, the scope of the variable sum is the add function, since that is where it was declared. Additionally, the scope of another variable sum is the main function, since that is where it was declared. Finally, the scope of the diff variable is the subtract function, since that is where it was declared. Now, let's talk about the two classes of scoping that are commonly used by programming languages. These classes essentially describe how entities treat their environment and how they determine which declaration to refer to based on the program's structure or call stack. The first scoping class is called static scoping, or sometimes called lexical scoping. This type of scoping is the one most commonly used due to its ease of use and general readability. In static scoping, spatial relationship between entities is emphasized. When searching for variable declarations, the compiler will search for the closest scopes first and spread out to larger enclosing scopes until it finds a declaration. Alright, let's have an example. Okay, suppose we have this program here which will print the value of x based on static scoping. If we look at the main function, we see that it calls the function g. And then g calls the function f, and then the function f returns x to g. And then g returns the value of x as represented by f to the main function. Now, the question is, what would be the value of x? Let's analyze it some more. In static scoping, we begin with local sub-procedures, then spread out to larger enclosed scopes until we find a declaration, right? So, in this case, since f is the one returning x, we have to find the declaration of x with respect to the function f. Locally, we can see that there is no declaration present in f. There's only this one statement, which is return x. No declarations around, which means that we have to spread out to the larger scope enclosing f. And the larger scope enclosing f would be the global scope, since, yeah, it's the global scope. There, the compiler finds the declaration int x is equal to 10 and assigns it to the x in function f, thus resulting in 10 being the output of the program. See, if we compile this program, we're going to be given the number 10. That's the output, 10, which is the value of x based on the global declaration. If we were to put a declaration within the scope of f, such as int x is equal to maybe 2, what's going to happen is 2 is going to be the output because when the compiler scanned the scope of f, it found a declaration immediately. So it didn't have to spread out to the larger scope enclosing f. All right. So with that done, let's move on to the next scoping class. The next scoping class is called dynamic scoping. It is a fairly new type of scoping and only a few programming languages use it. Thus, it's also the least preferred out of the two scoping classes due to the general unfamiliarity surrounding it. In dynamic scoping, the compiler does not base on spatial relationships. Instead, it is based on the calling sequence of the subprograms. The compiler scans the call stack and takes the top node of the stack. Okay, so let me demonstrate using the same program that we used, except I can't run this anymore in terms of dynamic scoping because, well, the C language uses static scoping. We're just going to have to use our imaginations for this one. Okay, the sequence starts with the compiler scanning the global scope and finding the declaration int x is equal to 10. So this is based on the call stack or the running sequence of the program. It starts with compiling the global scope, finding the declaration and int x is equal to 10. Then it proceeds to scan the main function, which calls the function g, and in the function g, there's a declaration called int x is equal to 20. So this one's going to be put at the top of the stack. The first declaration in the stack is this one. Essentially, if we visualize this, it's going to be like this. This is the stack. And at first, the top of the stack is int x is equal to 10, right? Then, when the compiler came across the second declaration, which is int x is equal to 20, it added that declaration to the stack, and therefore the top of the stack is now int x is equal to 20. Okay? This is an important detail because when the g function proceeds to call f, okay, let's remove this because that's irrelevant. This is the original program. When the g function proceeds to call f, we know that the compiler will be looking for a declaration to match with return x. So where does it find the declarations to match with return x? It looks for it in the call stack. It proceeds to get the top node of the stack, which is int x is equal to 20, and assigns it to this variable. So if we were to run this in terms under the context of dynamic scoping, it's going to output 20 instead of 10 because this was the one that was assigned. So that's essentially how dynamic scoping works. I suppose that's it for my introductory discussion to scopes. I'm now going to pass the mic to the next reporter who will be further discussing scopes and discussing its relationship with lifetime.
So, hello everyone, I'm Guy Evan Ocon and I am going to present to you the scope and lifetime of a variable. So yes, let's begin. Just an overview, scope and lifetime of a variable are very much related to each other, but still, there are some different properties associated with them that makes them distinct. Just an introduction. The scope determines the region in a C program where a variable is available to use, while the lifetime of a variable is for how much time a variable remains on a system's memory. Let's set an example. So here we have our real-life representation of the topic. Scope and lifetime can be understood with a simple real-life example of Netflix and Amazon Prime. So there are movies, TV series, present on this platform that have local and global scope. Movies that are based on local languages like Japanese, Korean, uh, or and such have a limited scope and can be watched in a limited area, while movies with global languages like English have a global scope and are available throughout the world to watch. So in this slide, our local scope here is the Gagamboy, a Filipino film. Uh, this film can only be watched here in the Philippines. That is why it is represented as the local scope. While on the other hand, the Spider-Man, it is represented as the global scope since it is spoken in an English language. Uh, it is spoken in an English language, which is a globally accepted language. Uh, Next is that these movies also have a lifetime. And once the lifetime is over, these movies are removed from the streaming platform. So let's dig deeper. Our first topic is scope. Uh, scope Scope is defined as the availability of a variable inside a program. There are four types of scope. The first one is the file scope. The second one is the block scope. The third one is the function scope. And the last one is the prototype scope. So the file scope of a variables in C is defined as having the availability of the variable throughout the file or the program. It means that the variable has a global scope and it is available all around for every function and every block in the program. So let's take a look at this code, the sample code. Excuse me. So a global variable x is declared having here the wait here global variable x is declared having file scope. The main function and the function are able to access the variable x because it has file scope. In the code, we have increased the value of x by 10. Yes. Now the x, if we compile this code, the value of x will become 20 since it increased 10 coming from the global variable x is equals to 10. Next, here in the main function, the value of the value of x here will now be equal to 50 since the x here in the function will be um, will be stored in the main function. So 20 plus 30 is equals to 50. Oh, excuse me. We can see from the output that the x preserves its value 20 after the changes made in the function because it has file scope. And the second one is the block scope. Block scope of variables in C is defined as when the variables is having a limited scope and the memory occupied by the variables will be deleted once the execution of the block ends. The variable is not accessible or available outside the block. So again, let's take a look at this code. In the above program, the sum variable is having block scope here. We can access the sum variable outside this block where sum is declared. If we uncomment this printf function here, uh, then the compiler will throw an error on undeclared sum variable in the current scope. So let's try it in dev C. Function. So let's run this code. Yes, as expected, the compiler noticed an error in the code since the sum variable here is not accessible in this part. It is only accessible in this block. Because again, it is a block scope. Do you understand? Let's move on to the next one, the function scope. So function scope of variable in C begins with a left curly brace and ends with a closing right curly brace. A variable declared inside the scope has a function scope. It has been allocated memory when the function is called, and once the function returns something, the function execution ends, and with it, the variable goes out of scope. Alright. Let's take a look at this code again. It's another code. We can see in the output that if you run this code, there will be a compilation error. It is because we are using an age variable outside the function from where it is declared. Compiler has thrown an error because age variable is not available outside the function, as age variable only has function scope. So the compiler throws an error because the code function here, the age, is only available in this function only. Sorry, in this function only. Um, it is restricted in this part since it is a function scope. Okay. Next, it is still under the scope. Next, we have scope rules. Okay. Scope of variables in C also have some rules demonstrated below. Variables can only be declared on 3 places in a C program. So variables that are declared inside a function or a block of code are known as the local variables. Variables that are declared outside of any functions are known as the global variables. Usually at the start of a program. Excuse me. And the third one is the variables that are declared in the definition of a function parameters at its formal parameters. So the first one of the scope rules, local variables. When we declare local variables inside a function or an inner block of code, then these variables are known as local variables. They can only be used inside the function scope or the block code. Again, let's look at this code here. We can see in the output that if we run this code, there will be an error showing us because we are using A and B variables outside the block. Yes, here in this part. So again, in the previous slide, we have discussed that block scope can only be accessed inside the block. Since we use these two variables here outside the block, it will commit an error. Yes, that is the local. Yes, that is the local variable. The local variable can only be accessed in a certain function or block of code. It cannot be accessed in all the functions available in the source code. Excuse me. Next is the global variable. When we declare variables outside of all the functions, then these variables are known as the global variables. These variables always have file scope and can be accessed anywhere in the program. They also remain in the memory until the execution of our program finishes. So let's look at this code here, showing us the global variables. So as we have declared a side variable outside of the main function, it has file scope, or it is known as the global variable. So again, global variable can be accessed in every part of the program. Yes, and it is and then it is uh, put um, at the start of the program. Uh, uh, Here we are using side variable as we're using side variable to calculate the area of the square in the main function. Yes, here is the solution. Uh, the side variable here is the global variable. Next one, the formal parameter. When we define a function and declare some variables in the function parameters, then these parameters are known as formal parameters or variables. They have function prototype scope. So again, let's look at this code. The- Uh, uh, we have here in this code, we have defined a function square. Mm, to calculate the square of a number. Then the int n variable in the square function acts as the parameter. Now it is also, where's the picture? The int n here is the formal parameter having function prototype scope. Again, the formal parameter here is the int n inside the square function. Okay, let's move on to our second topic, the lifetime of a variable. So, um, lifetime of a variable is defined as for how much time period a variable is occupying a valid space in the system's memory, or lifetime is the period between memory is allocated to hold the variable and when it is freed. So a variable in the C programming language can have a static, automatic, and dynamic lifetime. So the first one, static lifetime. Objects or variables having static lifetime will remain in the memory until the execution of the program finishes. These type of variables can only be declared using the static keyword. This is me. Local variables can also have static lifetime. They survive as long as the program runs. Uh, so here in this code below, the count variable will stay in the memory until the execution of the program finishes. Yes, and let's move on to the next slide. Uh, Automatic lifetime. And variables declared inside a block having automatic lifetime. Wait. Objects or variables declared inside a block have automatic lifetime. Local variables, um, those defined within a function, have an automatic lifetime by default. They arise when the function is invoked and are deleted together with their values once the function execution finishes. So in the code, in this code below, the auto lifetime var will be deleted from the memory once the execution comes out of the block. Yes, the third one is the dynamic lifetime. Objects or variables which are made during the runtime of a C program using the dynamic memory allocation concept using the malloc calloc function in C or the new operator in C++ are stored in the memory until they are explicitly removed from the memory using the free function in C or the delete operator in C++, and these variables are said to have a dynamic lifetime. Uh, the memory block variable pointed by the pointer will remain in the memory until it is explicitly freed or removed from the memory or the program execution ends. Yes, I think it's familiar to you guys since we've encountered this last semester, in our previous semesters, I think. Mm-mm. So, um, I think that is all. And Thank you for watching. Um, let's move on to the next reporter. Thank you, guys.
Hello, my name is Aliana Kristavibama, and I am going to present to you about the referencing environment. So referencing environment is one of the main elements in data control. When we say referencing in research, that would mean that we are acknowledging the source of whatever information we are going to use in our paper by citing the sources. So when we look at the references in the part of the research paper, we know that the links or the sources there are used inside the paper. Now, if you talk about computer programming, that would mean that we are looking at the variables that are to be used in the code. So we are referencing the variables we could use. And we know that variables could be declared locally, non-locally, globally, or it could be predefined. So the definition of referencing environment is it is the collection of all names that are visible in the statement. When we say visible in a statement, it refers to the associations a subprogram has access to during its execution. In layman's terms, that would mean all the names that a particular part of the code could use. So referencing environment could be local or it could be non-local. For local, these are the set of associations created on entry to a subprogram that represent formal parameters, local variables, and subprograms defined only within that subprogram. So just remember for local referencing environment, we are just referring to the local variables or just the function that are created inside just the variables that were created inside the function. But if it were created outside the function, that could be either be global or if it's not created or just directly defined, it could be a predefined one. So let's look at this. So in this part of the function, int a and b are the local variables of sub1, int b, c are the local variables of sub2, and cd are the local variables of main. Now for the non-local referencing environment, as I've said before, these are the variables that are declared outside of the function. These are the set of associations for identifiers that may be used within a subprogram but that are not created on entry to it. So it could be global or predefined. So global referencing environment are the associations created at the start of the execution of the main program and can be used by the subprogram. So when we create a C code, these are the functions, these are the variables that you could see at the topmost part of the code. The one that are outside of every function there is. There's like define blah 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 like that or it then followed by a whole lot of codes just just the global variables. They are considered global since every function there is under that could use the global variables. So for the predefined referencing environments, these are the identifiers that are defined directly in the language definition. Any program or subprogram may use these associations without explicitly creating them. So when we say predefined, just the predefined variables that these are the variables that come with the language. Like in Java, if we are going to use date, we are not going to define what is date anymore because it is already predefined there. So when we use date, it would return current date. And there are other predefined variables in each of every languages. So if they are grouped together, they are predefined referencing environments. So when we group together local and the non-local referencing environment, we would form just the referencing environment. So let us look at the referencing environments for static scope language. It is previously discussed in static scope languages that searching for a given variable name starts with looking inside a subprogram, which means we are locally searching the declaration of that name inside the subprogram. And if no declaration is found locally, we would move searching on larger enclosing scopes until a declaration is found. Thus, the referencing variables, as I've said here, these are the local variables plus the visible variables in all of the enclosing scopes. To better understand the definition, let's look at this example. So let us analyze this. Let us see what are the referencing environments here based on static scope language. So we could observe that this code has 4 execution parts, so begin, end. So this sub 1, it's going to execute this part. The sub 2 is going to execute this part. And sub 3 is going to execute this part. And so on and so on. So there are 4 execution parts, or there's statements in this code. To see the referencing environments, I'm going to first enclose this in their proper scopes to better visualize. So for example, function is going to until here. The sub 1 is until here. The sub 2 is until here. And sub 3 is here. Now let's look at the first part, which is this sub 1. As you can see, x and y are the local variables of sub 1. So we add them to the referencing environment. Now, going outside of sub 1 is example, the function example. And the function example has this as a and b as its variables. So the sub 1 could access x and y, and it could access AB from the example. Now next is for the sub 2. So looking at, next is the second part. So this is the sub 3. So looking at this function, we can see that x is locally defined here. Now going outside this function, we have sub 2. But as you can see, they have the same variables. And one thing to remember that in static scope language, if a local declaration of a variable is found inside the subprogram and is also declared at the parent or the ancestor or of the subprogram, then the variable of the parent will be hidden since the searching priority goes from local enclosed scopes to larger enclosed scopes. In other words, redefining a variable within a subprogram hides the original association during the execution of the program. To better understand that, I'll just going to give an example. So for example, the x here in sub 2 is equals to 5, and the x in sub 3 is equals to 3. So when this part of the code runs, it is only going to use the x equals to 3 declaration, since we are giving more priority to locally defined variables. So if they are the same, these are not going to be used. So In other words, it's just going to be hidden. Now, going outside the sub2 is the example. Which have A and B as the variables. So back in here, so the second part of the code, the second part could use x as an integer, x in sub2, no, could use x in sub3, x in sub2 will be hidden, and could also use AB from the example function. Now for the third part, which is this part. So this enclosed scope is from here to here. So we could see that it has x as its predefined integer. And going outside this function is the example function, is AB. So sub2 could use x from sub2 and AB from the example. Excuse me. Now for the fourth part, which is this part, as you can see, it's already it's part of the biggest scope in here. So it could only use the scope and the variables in this particular scope. So it could only use AB from the example. Now let's move on with the dynamic scope language. So the referencing environment in dynamic scope languages are the local variables plus all visible variables in all active subprograms. So active subprograms are those who have started their execution but has not yet terminated. If we could remember, dynamic scoping is based on the calling sequence of subprograms. Therefore, the search process for a variable starts from locally and then to the subprogram that calls this subprogram. For that, we have an example. So in this code, we have three parts. We have three statements, which is in sub1, in sub2, and sub3. And you can notice that sub1 is called here in sub2. I'm going to just drop it. So sub1 is called in sub2. And sub2 is called in main. Main is not called by anyone, so let's just start with main. Now, as you can see, in main, could only access these variables. And since main was not previously called by any function, it only has these variables as its referencing environment. Now let's move with sub2, which was called by main. So it can access B and C, and it could access the variable of the subprogram that called this sub2. So sub2 was called by main from here. So that means sub2 could use these variables from the main. And as I've said before, we are going to give priority on the local variables or the variables that was recently declared. So for this we have B and C, and C was declared in main, but C was declared in sub2. So we are not going to use this declaration from main. It's just the D. Now in the first part, sub1 was called by sub2. So the sub1 could access the variables in sub2. And since sub2 was called by main, then it means sub1 could access the variables in main. Just a caterpillar who's calling who, and just that is. So back, so we have AB as our local variables. And since it's called by sub2, we could access sub2. B was locally defined That means we are not going to use this B here, just the C. Then sub2 was called by the main, and C was declared here. So we're just going to use the recent declaration C. So we're not going to use this C here, or not really recent, or just the closest declaration to the subprogram that we are going to use. We're not so back to the topic. So C is not going to be used in main since C was declared in sub2, and we have D. So that means sub1 can use AB, can use C, and it can use D from main. Just remember that in dynamic scope language, we are going from locally and moving to the subprogram that calls this subprogram. So now why do we need to know about referencing environment? So for me, the importance of referencing environment is more on its practical uses. If you know what variables this particular part of the code or function or the subprogram or etc. would use, it is easier to understand the flow of the code based on what scope that you are going to use to see the code, either by static, static, or dynamic. So I think that is it for this presentation. And here are the references that were used. So thank you for listening.
Hello everyone, good day. I hope everyone is doing fine. I am Julian Marza, and before I introduce the topic that I will be discussing for today, I have a question for everyone. It's an easy question, so don't worry. Now, imagine a problem within a program wherein we need a variable whose value will never change, no matter the operations done to it. What do you think should we use? Now, obviously, we would need to use some named constants to address the problem. And obviously, my topic is about named constants. Now, I think, or at least I hope that everyone is already familiar with named constants, about what they are, what they're for, and how they are used. But for the sake of this peer lecture, I will be going over the important details that we need to remember when dealing with constants. So let's get started. As the name suggests, named constants are variables that are initialized to remain constant throughout the entire run of the program. When associated with an identifier, a constant is said to be named, although the terms constant and named constant are often used interchangeably. This is contrasted with a variable, which we all know is an identifier with a value that can be changed during normal execution, i.e., the value varies. Next, a named constant has three components. It has a name, type, and value or literals. Now, for example, suppose we have an array and we want it to have a fixed number of elements. We can use constants and name the constant max length or max size or some other name. It's fine. For the type in the example I just gave, we would have to use the int variable type for the integer. And of course, we have to assign a value to the constant. So named constants typically use the following syntax. This bit right here, different programming language have different ways to define constants. We will look at a few examples in the next slide. Next, it's normally followed by the type, name, and then the constant expression. Next, we have named constants in different programming languages. First one, which I think we are most familiar with is C++ or C. They both define named constants the same ways rather. With using this hashtag define or the preprocessor directive and this const keyword. Now, when they define constants using hashtag define, there's no need to put the variable type anymore and no need to use the equal sign. Now, for the const keyword, as you can see, it's used for C++, C, C#, Java, and JavaScript with just little variations among them. Like for the JavaScript, there's no need to put the variable type anymore. Now, meanwhile, the Swift programming language, instead of the const keyword, they use the let keyword. Now, you can just search how to define constants in different programming languages, but this is how they typically go about a keyword, the type, the name, and the literal or the value. Next, rules for naming constants. Now this part, it's basically the same with naming regular variables, but I will still go over each one. So the first one is the name can contain alphanumeric characters, lowercase and uppercase, and the underscore. Now, even though lowercase letters are permitted, it is advisable to use only uppercase letters. This helps you to visually distinguish constants from variables. Now, constant names are case sensitive. Names cannot start with a number. No space characters are allowed. And lastly, a constant name is usually chosen in a way that describes the meaning and the role of its contained data. So as you can see, they're pretty much the same as, like I said, when you're naming a regular variable. Now for the next part, I will be demonstrating for a little bit how to use named constants. So here we have a very simple C program wherein we can see we have an int constant int val, a named constant float val, char val, and string val. Now, it's very straightforward. It's very simple. Let's try to run it. So as you can see, integer constant 10, floating point constant 4.14, character constant, string constant is ABC, so it checks out. Now let's try to reassign the int val constant variable. Paste. So let's try to run it. Obviously, we're gonna have an error rather. We're gonna have an error called assignment of read-only variable, which occurs when we try to assign a value to a read-only variable, which is this constant right here. So you really can't change the value for the constant, the named constant. Now, following that very short demonstration of using constants in C, we're gonna answer the question, why do we use named constants? Why can't we just use normal variables for everything? Well, named constants or constants allow the programmer to give descriptive names to recurring frequent values. And one advantage of this one is, should the given value be modified in the source code, it is sufficient to modify the declaration statement of the constant instead of looking up all the occurrences of the value. So I guess that's it for named constants. I know it's a fairly simple concept to grasp, but named constants can really help us to code more efficiently and more effectively. These are the references I used for this presentation. And thank you so much for listening and watching. And I hope you learned something new or at least reinforced your previous learnings in today's video. Thank you.